So, guys, welcome all of you to this YouTube live session. So, today we are going to discuss computer organization and architecture with respect to b.tech curriculum. Now, before swimming into the computer organization and architecture area, it will be useful if we know like in which direction we have to swim, because it's a vast syllabus. It's a vast syllabus. We must know in which direction, at what depth we have to go. So for that reason, I have taken the syllabus first of computer organization and architecture. Then out of that syllabus, we will look out what are the most important topics frequently asked in PYQ. That is nothing but previous year question. So first, the agenda is like that. This session will go like that. I'll tell you the syllabus first. For every unit, important part I am going to tell you. Out of those part, I am going to tell you what are all the important topics which have been asked frequently. At least I have taken 4 to 5 year papers. Today, I am going to cover Unit 1 important topics in computer organization and architecture, as well as the PYQ asked from those important topics. Let's start our journey, guys. Okay? The fundamental thing is what is the textbook we are going to follow. If you want to refer the textbook is M. Morris Mano. But still, if you want to go much more, so 2 more extra books are there, Carl Hamster and William Stalling. These 3 books are sufficient to cover your entire b.tech syllabus. After that, let us go in Unit 1, what are all the important topics present in our syllabus. If you see over here, guys, in Unit 1, all about your digital computer. From the digital computers, we will come to know about the registers, how register transfer their data through bus. Then in the second part of a Unit 1, we will come to know the basic computer organization and its design. In the third part of a Unit 1, we'll know what are all the micro operations present in a basic CPU, like arithmetic micro operation, logical micro operation. These things we are going to see in Unit 1. They are the important topics. Now let us see in Unit 2 also. In Unit 2, it's all about your micro program. That is nothing but your control unit. How the addressing mode is all about, what are all the instruction format, all these things we are going to see in Unit 2, right? So about CPU, about control memory, how to design your ALU, how to design the control unit, these things we are going to look after in Unit 2. If you see Unit 3, that is the most interesting and the most gaining when it comes to the marks point of view, then Unit 3 is the most gaining topic. It's a most gaining chapter. Gaining in terms of what? Gaining in terms of knowledge, gaining in terms of marks, gaining in terms of interest. Unit 3 is really interested because it's about data. It's about data, how you represent data. So it's about data representation. In the data representation, what are all those things? So we'll start from the computer arithmetic. We'll look at the different data type. Then we'll see about the fixed point numbers. Then we'll see floating point number. The moment I say fixed point number, that means I'm talking about your unsigned number. In the signed format, I'm talking about 1's complement, 2's complement, all those things. Then the moment I say floating point number, that means I'm talking about how you are going to deal with decimal numbers, real numbers, how you are going to deal with that, how you are going to make the large number in less space. How you are going to deal with those numbers, we'll study in floating point number. Not only we will study this part also, how to add, how to subtract, how to multiply, how to divide a floating point number, right? These addition, subtraction, multiplication, division, all these things we are going to do in computer arithmetic also, right? But with a fixed point number. After that, there is something called as a multiplication algorithm, very popular algorithm called as a Booth's algorithm. Very popular question every time, like the b.tech, whosoever the people who is designing the b.tech paper, they love to give from this part, Booth's algorithm. Like almost every paper I have seen, Booth's algorithm question is there. And it's really, really interesting. It's really interesting, guys. It's just a sort of algorithm of 3-4 lines, that's all. After that, addition and subtraction of a binary number, what all the number systems are there. Majorly, we will study 4 types of number system: binary, octal, decimal we already know, right, and hexadecimal. In these 4 number system, how to add, how to subtract, if the carry is coming, how to deal with that carry, all those things we are going to look after in addition and subtraction inside unit 3. You are with me. Guys, whatever the topic I am showing you over here, they are all the important topics. They are all the important topics. After that, unit 4 will come. Unit 4 is about your organization. Unit 4 is about organization. Architecture part you done. Architecture you did it. Now this is the right time for the organize. Now input output organization. In this part we will look at input output interface. Then we will look at mode of the transfer in IO module. Then here comes the memory module. In memory organization we will look after the memory hierarchy. Memory hierarchy, like whatever the suitable unit present inside the memory for storing the data. It may be your RAM, ROM, it may be your secondary memory, hard disk. So these things we are going to see in memory organization part. Then after learning all these concepts, we will learn how to deal with main memory, how to deal with auxiliary memory. Okay? Now at last, we finished our computer organization, we finished our architecture. Now this is the right time, to enhance your process. This is the right time to enhance your process. How you are going to enhance your process? It comes in unit 5. Unit 5 is all about your enhancing. How we are enhancing, sir? There is a topic called as a pipeline and vector processing. In a pipeline and vector processing, we will learn how to enhance the process, how to enhance the processor. Now after that, the moment we learn this particular topic, in our hand, what is there? Architecture part, organization part. Organization part we came to know, architecture part we came to know. We have enhanced it also. This is the right time to understand about one specific processor. Now, in most of the syllabus, 8086 processors have been added. So we will study all the new unit, all the module in 8086 processor, because the moment we are reaching here, we came to know about all the important parts inside the processor. Right? We came to know about the CPU part, we came to know about the IO part, we came to know about the memory part. This is the right time to understand the entire microprocessor. That's why it has been written inside the unit 5, not in unit 1. Right? Now, after that, the moment you understand it, this is the right time to develop, to know how you can program that processor, which comes under the assembly language programming with 8086. How can you play with that processor? Then only this is the real meaning of understanding the computer organization and architecture, isn't it, guys? Okay, now till now we have seen what are all the important parts in our curriculum. They all are important. They all are important. I have selectively picked up those topics which have been frequently asked. Now, you know all these things. Over here, I want to show you inside a paper. I have taken 4 to 5 year paper. In those 4 to 5 year paper, so like this is the paper for ACE College. So over in this paper, if you see, I am going to pick what are all the questions present in unit 1, not in unit 2, not in unit 3, not in unit 4, not in unit 5. I am going to pick out the question present in unit 1. And then like that, I will do the same process with 4 to 5 paper. After that, we will analyze what is the topic frequently asking. I will show you first and then I will do. Look this ACE paper 2022. If you look at these two sections, these two questions, it is from unit 1. So I am not going to read all the questions because right now I am assuming you are a void means we both on the same platform, we don't know much about anything. So I am just picking out main points so that when the actual topic will come, I can recall you. Please recall, this question has been asked. So question 1, important point, look here, arithmetic logic shift unit. Okay, arithmetic logic shift unit. Okay, then See, list out and discuss the logic micro operation and shift micro operation. Again, arithmetic logic shift unit, he ask logic micro operation and shift micro operation. Okay. Then if you see in the March 2002 paper, look at the first question from unit 1. This is the question from unit 1. He is asking to design bus system, One in previous paper asked for the arithmetic logic shift unit, how it is performed. In 2022 paper, in the March 2022, they are asking design a bus system using 3 register, maybe some K register, maybe 4 register, like that they are asking. But design your bus system, how you will design, like that. Okay. After that, I have taken some paper from JNTUH also. In JNTUH, like explain the detailed computer design and computer architecture. Okay, this is the first question. Next, they are asking different, explain the following, register transfer, all these things they are asking. Okay, fine. After that, if you see March 2021 paper, they are asking discuss functional unit of digital computer. Just recall, in 2021, they are asking functional unit of digital computer. And previously, again, if you see first question, they are asking detailed computer design and computer architecture. Like their focus is on, please you tell us, do you know digital computer? Do you know digital computer? This is what their focus. That's why they are asking many time. Okay. So like in this paper also you can see functional unit of digital computer. Okay. If you see question number 2, they are asking design 4-bit arithmetic logic circuit using 4 full adder. Okay, we will see all these things. Now, in October 2020 paper, they are asking discuss the bus system. Again, see, again the bus word is referring again and again. So this bus system is really important. Computer design is really important. That's what they are asking again and again. Micro operation, really important. That's what they are asking again and again. So these 3 points are really important. So then they have asked some question based on the micro operations only. This is the numerical question they have asked in 2020 on the micro operation only. Now, let us start with one of the possibility of asking the same question. Question 1 is saying explain in detail computer design. The same question has been asked in the manner discuss functional unit of digital computer. The same question asked in the manner of draw block diagram of a digital computer and explain it. There are some of the possible way asking the same question. Do you know digital computer? Can you draw the block diagram? All these things. Now, guys, this is the right time to deep dive. So before telling you the solution, let me give you the introduction. Then from the introduction point only, you will get to know how to write your solution. So see, again I am going to show you. These 3 points are really important in unit 1. Register transfer, how you are transferring your data through register via bus. What are your CO design? What is the block diagram of your computer? What are all the micro operation? These 3 are really important topic in unit 1. So our first question on unit 1 is from this part. Can you draw? It's from this part. Can you draw the block diagram of a digital computer? Now, let us study that part. But before telling you the introduction part, let us look at how does our computer motherboard look like. Then we will have very much clear-cut idea what they are actually asking and where we should go. Let us look that part first. So internally, how does motherboard look like? You need not to think we have to draw this particular motherboard in the exam. No. I am just giving you the idea first. You please observe first. Then if your observation is correct, you can make your answer like anything. First, just give your observation in your motherboard. There are some points. Let us understand those points. Let us look at this particular section inside the motherboard. Inside the motherboard, this particular section is known as RAM. Inside this section is known as RAM. Then there is a section called as slots for hard disk, hard drive. This is a section for hard drive. Then there is a section for your sound cards. This is a section for your sound card inside the motherboard. Now, there is a section for your graphic cards. There is a section for your graphic cards. Like a person who do the high live streaming, crazy gamers are there, right? So, or like you want to edit some high quality video. So, you need this graphic cards, right? Vector, a huge number of data processing, data mining, they need this graphic cards for sure. GPU is required over there. Now, if you see in this part, in this section, that is a section connected for all your USB, whatever the peripherals you are having, this section is responsible for that part. Now, here comes the actual thing. What is that actual thing, sir? The picture is revolving around that person only. Who is that person? Who is that person? That person is nothing but CPU. That person is nothing but CPU. Where is our CPU? Where he is? He is inside here. Here our CPUs lies. Now this particular slot is your CPU slot. Maybe Intel 5, Intel generation 5. Maybe it is your AMD processor. AMD will put here like that. It's your CPU slot. Now hope you have an idea. Now computer organization architecture is telling you, you please know how your CPU slot. You please know your CPU. You please know how your I/O and memory are connected, how the data transfer take place. You please know all these things. Inside the CPU, you please know what are all the addressing mode. All these things we have to know. So unit 1 and unit 2 more or less revolve around your CPU only. Unit 1, unit 2 more or less revolve around CPU only. So let's focus yourself in this part. You have a clear cut of a picture of motherboard. In a motherboard, now we have to focus in this area. Now let us look at CPU. So the question was all about, do you know digital computer? Do you know digital computer? From here our answer is start. Our answer is start. So if you see any digital computer, we have a CPU, we have an input output module, we have a memory module. CPU, input output module, memory module, they all are connected. How they are connected? Via some lines. A set of those lines are called as bus. In this particular slide, you can see CPU is there, you can see I/O module is there, you can see memory module is there. They all are connected. How they are connected? Via bus. This is your bus. What is bus? All these things we are going to study in unit 1 only. I will show you everything. But this is the high level diagram of your CPU, memory, I/O. Okay sir, okay, CPU is there, then what is that? Okay, CPU is there. Inside the CPU so many sections are there, right? Memory is there. Memory is also so many of type, right? Input output module is there. Input is there. Input is going to be processed and then output is coming out. So this entire flow, input is coming into the processor and now processor is following the input, and now after giving some process, it is showing on the output. This entire flow diagram is all about your digital computer. If you understand this pattern, digital computer over. Now let us deep dive into this diagram. Let us see inside what the diagram is all about. Let us see that part also. If you see this entire structure, CPU is going to be linked with memory. It is the same as previous diagram, but I am zooming it more. It is a previous diagram only, like CPU, I/O, memory. Now I am zooming it more, so that you have a clear-cut idea how the things are going on. Okay, you got to know CPU here, you got to know memory here. Now, what CPU and memory will do alone? No, nothing. You have to provide input something, and then it has to be shown on the output. So input unit is required for providing the input, and that particular input is going to be processed, then it needs, if it is required to store that data, it has to be stored inside the memory, and it is going to be the output. I think till now everything is okay. Now let us understand the CPU bit more. Let us understand the CPU bit more. In a CPU, we have 3 sections. In a CPU, we have 3 sections. This particular section is written here ALU, Arithmetic Logic Unit. As the name suggests, arithmetic logic unit used to perform the arithmetic operation, logic operation. That's why the name given. So these operations are performed under the control of control unit inside ALU. After performing the operation, the data has to stored somewhere, need not to discuss over here. That is there in the register concept, where the data after processing needs to be stored. But what ALU is doing, this is important. What ALU is doing? It is performing your calculation. Calculation for what? Calculation for your arithmetic, calculation for your logical part. So this is responsible for ALU. Then after that you can see some yellow square is there. Is it for design? No. This yellow square represent, okay, inside the CPU also there is some storage unit. Inside the CPU also there is some storage unit. Those storage unit are nothing but your registers. They are registers. Now these registers are also categorized in many ways. Broadly, they know by the special purpose unit or general purpose unit. So every CPU will have some special purpose register and general purpose register, right? So in the special purpose, general purpose, these all are the categories which we have to study inside the register section, okay? I think in the unit 2 these things will come. Then their section, this control unit. Again, control unit is responsible for controlling your CPU. It will give all the direction, what operation needs to be performed, which instruction is there, what to do with that instruction, like decoding of that instruction, performing the operation on that instruction. All these things needs to be done inside control unit. Again, control unit is the unit 2, right? Now, this is all about your CPU. Your ALU, if you came to know about the register, if you came to know about the control unit, on a higher broadly, I can say, okay, you know at least the structural view of CPU, structural view. Behavior view, we will see, but structural view you came to know. Having 3 parts, ALU, register, control unit. After that, it is the right time to discuss about the memory. In the memory 2 section, primarily it's a primary memory, secondary memory, primary memory RAM or ROM, secondary memory hard disk, like these things we already know. How memory CPU are linked? Using bus. Using bus. Not only memory CPU, even IO module also linked with the CPU using bus. Just to give you the flow, I have drawn the diagram like this. Absolutely fine. So this is how it looks like. Now, the point is, sir, yes sir, you told how this block diagram look like. You have zoomed that block diagram also, but still, some bullet points are always required while writing the answer. Yes or no? Now let us see those bullet points. Let us start with input unit and output unit. So let us see first input unit. What input unit is it? It accepts the data and instruction from the outside world for sure. Then convert it into a form so that our computer will understand. It accepts the data, then it is converting into the form so that our computer will understand. After that, supply the converted data to the computer system for further processing. Now the output, if I ask you the example, you know already, right? No need to discuss all these things, keyboard, mouse scanner, you know all these things in a very detailed way. Yes or no? Output unit the same. The output unit of a computer provides the information and result, right? So on the output, like your monitor, you all know, right? So this is the example you can give. Now ALU, broadly, ALU is nothing but your arithmetic part, is logical part. Arithmetic part nothing but addition, subtraction, multiplication, division. Logical part AND or NOT, XOR, XNOR. See, all these things we have to study inside the digital logic and design, which is another one chapter. So people say while studying COA, this is really important if you have a knowledge of digital logic and design. If you have a knowledge, well and good, otherwise we always go from the scratch. Okay, this is about ALU. Now let us see about CU, control unit. ALU gone, CLU. So it helps the computer system in process of carrying out the stored program instruction. If I ask you, stored program architecture is also known as, please tell me, one human architecture, right? Okay, so we study about one human architecture only, okay? We study one human architecture only, okay? So this is about CU, control unit, okay? It has to process the stored program thing. Then it interacts with both memory and CPU. Control interacts with both memory and CPU. At the end, what it is doing? It is directing all the module present inside the computer. It is signaling, it is giving signal to all the module present inside the computer, control unit. That's what the coordinates words comes into the between. The coordinates word is written because it controls all the module. Okay, fine. Sir, CU also. That means we came to know about CPU. If we know ALU, if we know CU, that means we know our CPU. Okay. That means what CPU is doing on a high level, it performs all calculation, it takes all the decision, it controls all the unit of a computer. The moment I say it performs all calculation, that means I am talking about ALU. The moment I say it takes all decision, it controls all unit of a computer, that means I am talking about CU. I think on a high level you are comfortable with this part. Now, there is something called as a memory unit, which is the last part. If you look at this memory unit, what this memory unit is doing. So, memory unit is nothing but it is storing your data. Inside the memory, what we are doing? We are storing our data, right? Now, in which format we are storing? Because it's a digital computer, we are storing in a binary format. Now, you can give in your answer, you know the primary memory also, you know the secondary memory also. In primary memory, you know RAM, ROM, in secondary memory, you know hard disk, like that, you can explain it. But our agenda is not to explain over here because these are really basic things. Now, the next point is, do you know how memory looks like? I think if you end your question in this format, if you end your question solution about the digital computer in this format, the examiner will be impressed like anything. Wow, what answer he has given. He knows the memory internally also. He knows memory internally also. Now, how can you very sure do you know the memory internally? For that reason, I am going to give you the example. So, if you look at your memory space, a very basic memory space I am going to show you. You please just forget that I am talking about some memory. Okay, you just forget it. Please tell me how many rows you can see inside this space. How many rows you can see? I think you are going to see 8 rows. 8 rows. Now I am asking you, in every row, how many bits are there? In every row, I think 8 bits are there. Yes or no? Okay, that means what? Okay, sir, in every row 8 bits, there are 8 rows. That means what is the memory space? I think you are giving me answer. Sir, it is nothing but number of cell is 8. Size of each cell is 8 bit. Sir, number of cell is 8, size of each cell is 8 bit. That means it is nothing but 64 bit thing. 64 bit. The memory space is your 64 bit. That means literally it is storing 64 bit. Or in other words, I can say it is nothing but 8 byte. 8 byte. Are yes or no? Now, if I see this 8 byte in another way, in another angle, if I see this 8 byte, I can write like this: 8 into 1 byte. That means I have 8 rows, and every row is having 1 byte. Okay, that is also fine. I have 8 rows, and every row is having 1 byte. That is also fine. We came to know about this part. Okay, sir, I came to know about this part. That means this memory section is of 8 byte. Sir, I know. Now my next question is coming. Do you know what is your RAM size? Do you know what is your RAM size? Some may say, sir, my RAM size is 4 GB. Some may say, sir, my RAM size is 16 GB, sir. Some may come and they will say, sir, my RAM size is like I am a crazy gamer. My RAM size is 32 GB, sir. Like that, you people will respond. Okay, then out of your responses, I am taking one of your response and I am asking you again, can you tell me, what do you understand by, what do you understand by 4 GB? Let us say you are a computer engineer, right? You know your RAM is 4 GB, but what you really understand by 4 GB? Do you know how 4 GB looks like? Just I have given you the enough hint. Please, can you calculate in your copy and can you tell in the comment section how the 4 GB look like? Can you tell me how many cells are there? That means how many rows are there? That means I am asking about how many locations are there in 4 GB. Okay, I think you are guessing right. What you are guessing, let me write here. You are guessing, I think, you are guessing, sir, 4 GB means 4 GB, as you said 8 byte, I can write 8 into 1 byte. In the same fashion, 4 GB you can write, sir, 4G into 1 byte. Sir, you can write like that. That means number of location what? Number of location what? Sir, G is 2 power 30, 4 is 2 power 2. That means number of locations are 2 power 32. Number of location is 2 power 32. And every location is having 1 byte. Every location is having 1 byte. This is what literally your 4 GB means. If I ask you, do you know now 16 GB? Your RAM is 16 GB. Do you know how many locations are there in the 16 GB? Sir, I know. I know very well. Because G is 2 power 30, 16 is 2 power 4, right? That means I have 2 power 34. 2 power 34 location I am having, and every location is having 1 byte. Now you came to know like how your RAM looks like. Yes or no? Now you came to know how your RAMs look like. Over here it is there. It is mentioned about your RAM. Now guys, this is about the memory space. You came to know about your RAM size also. Here if you want, you can end your answer. But still, now I am going to tell you how your computer is literally linked with your memory. You came to know about the memory for sure, and you are ending your answer over here, answer end. Answer end. Answer end over here. But now the next question is, sir, like your digital computer, now I understand. I understood your I/O module, I understood your memory module, I understood CPU design also. I understood CPU structure at least. I came to know how this memory structure look like. But still, rack your brain with respect to CPU and memory. Your answer ends here, but still let me tell you some additional point with respect to CPU and memory, which is useful for you for sure. Not with respect to exam, with respect to knowledge. With respect to knowledge, let me ask you one thing. If I ask you, what is your laptop operating system bit? What is the size of your laptop? How many bit your laptop is having? You will proudly say, sir, my laptop is a 64-bit computer. Some may say, sir, my laptop is 32-bit computer, sir. Now, my next question is, do you really understand what is 64-bit computer, what is 32-bit computer? If answer is no, look carefully, you will understand everything. In a basic CPU, you will understand everything. Now, for that, I have taken a heading called as rack your brain. Just screw your brain in this format. It is nothing like a screw. Just sit, relax and watch. Okay. Memory is there, already you have shown, but you have taken one more unit. Sir. That unit is nothing but decoder. Decoder you have already seen in your digital logic and design. In the digital electronics subject, you have seen decoder. What decoder is doing? If it is having an input, 2 power and output, yes or no? You have seen this part. I am assuming you know decoder. Then only I am going forwarding. Now I am showing you the correct way of memory module. In a memory module, every cell is going to be linked with your decoder output. That means, let us say I have 4 number rows. How many rows? I have 4 rows. I have 4 location. How many location are there inside my memory? 4 location. Now, I need to access this location only. So with the help of decoder, I can access. Because we know in a decoder, by providing your input, you will get one of the output. By providing input, you will get one of the output. This is already we know in the decoder. Why I am not explaining decoder? Because it's a digital subject part, right? COA prerequisite is you should know at least the basics of decoder, at least the basics of all the digital unit components. Okay. Assuming you know, now this is the right time. If I ask you, if I am providing here 0, 0, which location is going to be accessed? I think you are giving me the answer, sir, location number 0, because 0, 0 is nothing but location number 0. That means this location is going to be accessed. If I put here 0, 1, That means 0, 1 is what? 0, 1 is in binary, in decimal 1. That means which location? Location number 1. That means this location. Manually, if you count, this is the second location, but with respect to numbering, this is the first. This is the 0th location, this is the first location. Okay, fine. Now, if I give here something like, so this is something called as, it is written in this fashion, right? A0, A1. This is 0, this is 1. Okay, pardon me. This is 0, 1 is 2 actually, because it is A0, right? How you will write A0 on the LSB? I have written here 0, 1, 0, 1. 0, 1 means what? 2, 2. The moment I am giving 2, 2, that means this particular location is going to be addressed. With this binary format, this location is going to be addressed. Now let me take this one. 1, 0. That means A0 is 1, A1 is 0. With this particular binary format, which location? Which location? I think this location is going to be addressed. Okay, I'll come to that question. Like if I say my laptop is a 32-bit laptop, what should I really understood by that part? Okay, I'll come to that point. You please wait and watch. Okay, it's really interesting. It's a popular interview question also. It's a popular interview question also. Like people like in DRDO, in BARC, I have seen many interviews question like this. They will dig you inside this concept. So let us understand. It is nothing. You just see it. Okay. Now, if you really understood this part, if I provide here 1, 1, can you tell me which location? I think you are giving me the reasons. A third location, that means this particular location. Now I can say you understood why decoder is there. At a time you are going to access one location. How you are accessing? By providing input on this line. On this line. Now the next question is coming. Sir, you have given the input, but who is giving this particular input 0, 0, 0, 1, 1, 0, 1, 1? Are you are going to give? You are coming over there and you are writing here 0, 0? No. Who is going to give? I think you guessed it. The answer is CPU. CPU is going to give the location where to access, where to do knock, 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 knock. Hello, hello memory, I came, please open your door. Who will give? Who will give? CPU will give. Now this is how your CPU is attached. This is how your CPU is attached. The CPU is providing these addresses. Okay. Now if CPU is providing these addresses, can I ask you one thing? Can I ask you one thing? My question is, what is this? These are line. These are line. What these lines are doing? These lines are providing address. That means these lines are nothing but address line. These lines are nothing but address line. You know what these address lines, with the help of two line, how many location I am accessing? With the help of two address line, I am accessing 4 location. With the help of two address line, I am accessing how many location? I am accessing 2 power 2 location. That means 2 power 2 cells, you can say, or you can say 2 power 2 rows. Like many words are there. Okay. Now I'm changing my question. Now I'm asking you next question. Now I'm asking you, let us say if I increase my address line. Let us say if I increase my address line to 4. Right now I have 4 address line. Let us say I have increased like this. I have increased like this. This is A1, A2, A3. How many address line? 4 address line. Let us say I have 4 address line, guys. Can you tell me how many location with 4 address line? With 4 address line, I have 2 power 4 location. That means how many location? 16 location I can access. 16 location I can access. Okay, fine. Again, I'm changing my question. I'm asking you, can you give me if I have 8 lines, 8 address line? 8 address line if I am having, how many location you are having, how many cell you are having? You are going to say, sir, I am having 2 power 8 location. My CPU can access 2 power 8 location if 8 address lines are there. If 8 address lines are there, my CPU is going to access 2 power 8 location, sir. Okay, fine. You came to know about this part also. Like that we are going to understand a bit more. Okay. Now the next question is coming. I have. This is a really important question. I hope you clearly understand this part. I'm erasing it by hoping you clearly understand this part. Now, next question is coming. Tell me this. You have to give. I have 32 address line. Tell me, how many location your CPU is going to be knock? your CPU is going to be access how many location? 2 power 32 location? 2 power 32 location? Let us assume these are not 4, these are 2 power 32 location. Let us say this is the 0th location. The last one is 2 power 32 minus 1 location. Because we started from 0, that's what I have written minus 1. This is 0th, 2 power 32 minus 1. Okay, fine. That means they are all 2 power 32 location. Okay, fine. Okay, fine. That means I can access 2 power 32 cell. That means what? That means if every cell is having 1 byte, can you tell me what is your RAM size? If every cell is having 1 byte and I am having 2 power 32 location, what is my RAM size? Can you tell me? Please tell me. How can you tell your memory space? Just now we have seen how to tell memory space. Number of locations, how many? 2 power 32. Size of location is 1 byte. Can I say 2 power 32 into 1 byte is what? 2 power 32 is nothing but 2 power 2 into 2 power 30 into 1 byte. What is this? This is 4G. That means what? It is 4GB. Oh, that is interesting. We got it. 4GB. What is that? That means the moment you are saying, sir, my laptop is a 32-bit laptop, that means it is supporting 4GB RAM. If you are saying, sir, my laptop is 32-bit laptop, that means it is supporting 4GB RAM. The moment you are saying, sir, my laptop is a 64-bit laptop, it's a 64-bit laptop. That means it's a 64-bit laptop. It is nothing but 64-bit can access 2 power 64 location. Every location is having 1 byte. Are yes or no? That means this particular laptop which is having 64-bit laptop can access 4GB also. It can access 8GB also. It can access 32GB also. Now let me tell you one more thing. If your laptop is a 64-bit laptop, for sure, you might have more than 4GB RAM. Are say yes or no? If your laptop is 64-bit laptop, for sure, most of the case, you have more than 4GB RAM. It can access now. That's what it is the reason. Now you came to know what is the relation with this address line and the number of location present inside the memory. This is what we came to know till now. Assuming every location is having byte, which is a default nature, yaar. Which is a default nature? Default nature of a memory is every cell is having 1 byte. It's a default nature. If you go in the market also, you buy like this. Give me 4GB RAM. Give me like 16GB RAM. Have you ever asked like this? Give me 4 nibble RAM. Like this you never ask. Give me 4-bit RAM. No, because you know what is a memory unit. Memory unit is byte. Why? Because every cell is having 1 byte. That is the reason. Okay. So memory unit is in byte, but let me tell you one more thing. CPU unit is in word. Okay, there is some another concept related to CPU unit having word, memory unit having byte, but need not to discuss over here. But this is for your understanding part because we are discussing rack your brain. If we are starting computer organization and architecture, we must know how the CPU is going to knock inside the memory. We came to know about this part. Now the next part is coming. The next part is, sir, our register is having a data. Registers are having a data for sure. Now this data needs to become on the CPU or not? It has to process or not? For that, there again one more lines required. Those lines are nothing but your data bus. This line is called as an address bus. This line is called as a data bus. Again I am repeating, this is address bus line, this is a data bus line. Can I ask you one question? Can you see the direction? Address line which direction? Towards memory. That means CPU is having the authority for giving the address. Memory is not having that authority. CPU is Papa. He is Papa. He can give address. They all are children. They can only take address. That's all. But this part, data line is a bidirectional. Data may come from the CPU, data may come from the memory also. That's what, it's a bidirectional. It's a bidirectional. Now, how many bits you can see? 8 bit. That's what. How many bits should I lie over here? 8 line, because every line is responsible for 1 bit. If I take 8 line, then means at a time 8 bit. Every line is 1 bit taking. If I take 8 line, that means 8 bit at a time it can go. Now let me tell you one process from CPU to memory. You understood everything. Just give me one small scenario. Game over. My small scenario is this. Let us say I want to access this particular row, and I want to take the data from memory to CPU. The moment you are taking the data from memory to CPU, that is known as read. The moment you are giving data from CPU to memory, that is known as write. So I am taking the data from memory to CPU. That means my control unit will perform some operation or not. Control unit will give the signal or not. Control unit is giving the signal, please read. Read signal activated. And this read signal, in which module activated? In memory module activated. See, read signal can be done in the IO module, in the memory module. Over here, my intention is to tell you in the memory module. So read signal got activated. Now from where we have to read? Give that address in the address bus. Who is giving? CPU is giving. Let us say I need to access this one location. One location. That means what? 1 will come here, 0 will come here, 1 0 1 0. That means A0 is 1, A1 is 0. That means one location I can access. Now I have this data. Bring this data via data bus. Bring this data via data bus. Now via data bus, if I am carrying this data, where should I store? Inside CPU memory storage. What is the name? What is the name of CPU memory storage? The name of CPU memory storage is register. The name of CPU memory storage is register. Okay, fine. Sir, we got to know, like the data is coming. This is a 8-bit data for sure, and you are storing inside the CPU. We got to know this part. What is the data? Let me write it. We have stored somewhere, and this particular data is stored in some register. So let me name that register. Let us say this is a data register. Because till now I didn't told you what are all the instruction. That's why I am not naming it as an instruction register. Let us assume this is a data, and we stored it in a data register. Okay. Now this data register, or you can say some buffer register is there. Okay. We have stored in this register. Now this data needs to be processed. This data is having so much information. Maybe this particular data have some format. The data, let us say the data can be divided into 2 parts. That means this data is having 2 address format. Data can be divided into one part. Data is having something like 1 address format, like that. If I pronounce this data as an instruction, now I am again claiming it as, this is my instruction. Let us say instruction I can break down into 2 parts. How CPU will get to know? This is all about your addressing mode, instruction format. All these things will come in the unit 2. Addressing mode, instruction format, types of addresses, all these things will come in the unit 2. Till now I am just telling you how to read the data. Now data comes inside the instruction register. Now how to process the data, it is a unit 2 game. Everything is clear till now? Okay. Now I hope now you are so far clear how to read a data and from which path we are reading it. Are yes or no yaar? Okay, fine. So this is the entire part. Now if you really understood this part, let us do some aptitude question. Your b.tech, they are not going to ask this type of question, but this type of question is really important for some racking your brain. Just for your knowledge developing, this type of question is really important. Let us solve quickly. In 1 minute we will solve it, because you understood the previous slide. If there are 512 G location in the memory, then find the number of bit to represent each location uniquely. How many locations are there in a memory? How many locations are there? Can you tell? How many locations are there? The locations are 512G. These many locations are there, man. Now these many locations means what? These locations means like I have literally 2 power 39 location, because 5 and 2 is 9, G means 2 power 30, that means I have 2 power 39 location. If I have 2 power 39 location, how many bits required? How many bits required? Bits required is 39. How many bits required? bits required? 39. So this is the entire part. This is the entire part. The question was asking about find the number of bit to address each location uniquely is 39 bit. Did you understand it or you just solve it? Please tell me. Did you understood it or you just solve it? You please understand. 39 bit. Literally, let us say I need to place these 39 bit because lack of space I can't do it. Using this 39 bit, I can create 2 power 39 location. Can I ask you what is the name of location 1? Can I ask you what is the name of location 1? How can you represent in 39 bit? Arey, you have to tell, man. You will say this, all 0, the last one 1, the last bit 1. That means what? That means you are accessing the first location. In the 39 bit, you are accessing the first location. Arey, yes or no? Now that means you understood now the first question. Let us look at the second question. If there are 25 bits available to represent each location of a memory, then how many maximum number of location words can be addressed uniquely? Now the question has been reversed. They are asking how many bits I have. I have 25 bits. From this 25 bits, how many location the CPU can access? The location CPU can access is 2 power 25. 2 power 25. 2 power 25 means what? 2 power 25 is nothing but 2 power 5 multiply 2 power 20. 2 power 5 is nothing but 32. 20 is nothing but million. That is nothing but 32 million. 32 million location I can access, yeah. 32 million location I can access. That means now I am creating one more question in this question only. Let us assume I am exploring this question. My next question is, can you tell me if every location is having 1 byte, how many byte is there? 32 MB. I think now you are clear. If you understood these first two questions, this is the direct question, this is the reverse question, that's all. That means now you are very much clear with the topic known as digital computers. At least you have somewhat idea, right? Okay. Now guys, this is the right time to discuss about the second part from the unit 1 only. About this question. Explain in detail register transfer through bus. How register transfer take place? See, in unit 1 we have observed 3 topics are really important. First, do you know about digital computer? Second, how data is going to be transferred from bus. The third part about the micro operation. Now, over here, I'm discussing about how the data is going to transfer from register to bus. The possible way of asking the same question is explain in detail register transfer through bus, or discuss the bus system for 4 register and explain. Arey, these type of question have been asked in PYQ. That's what I have written here. Okay. Now, in order to understand this question, this word you should know, bus. This word BUS, bus. We should know bus. Then only we can answer it perfectly. So first of all, I am going to tell you your bus type. You have seen bus when I was racking your brain. You have seen that part. But let me tell you in some point format. Okay. The first and the fundamental question is, sir, why bus is needed? Why bus is needed? We have to understand it. Why bus is needed? Let me show you. Let us say this register want to transfer its data over in this register. 8 bits are there. 8 lines are required because at a time only one line may contain 1 bit. So fine, if 2 registers are there, 8 lines can do its job. But let us say in a computer, can you tell me, do you have only 2 registers? Do you have only 2 memory unit? No, there may be more memory unit. Let us say I have one more register. Now how you will, let us say this register want to transfer via this register. Now again you will add these lines. Let us say this register wants to add this register. He wants to transfer it. Again you will link up these lines. Let us say I have one more register. If you see over here, this register is transferring over here. You have added this line, these lines. Let us say this register wants to travel over here. Again you have added every bit, you have added one line. That means what? The moment the number of register are getting increased, it becomes clumsy. It becomes, very like it is not looking good, right? So just to prevent this particular scenario, bus is needed. Now, how the buses look like? So we know this CPU, we know this memory, we know this IO module. Our bus is linked. This entire is your bus only, because bus is having 3 major part. It is having so many lines, but having 3 major part of a bus. One line is responsible for, like one bus is responsible for address. One bus is responsible for your data. One bus is responsible for your control part, whether we have to read, whether we have to write, like that. So we have 3 types of line. One is control line, address line, data line. Can you tell me, data lines are one only or more than one? More than one. 32-bit CPU, how many? Address line, one only, more than one. More than one, right? 32-bit CPU, how many address line? 32 lines. Data line, one or more than one? More than one. That means data. Let us say I want to transfer 8-bit, 8 lines I have added. That means again more than one line. And you please remember, every line is taking 1 bit at a time. Right? Okay. Then control line is responsible for dealing part, the control signals. These 3 control lines, data line, address line, they are called as bus. I hope till now everything is okay. But let us explore these things first. Address line, let us know a bit more, like how to write in the exam. Let us know a bit more. Data lines, control lines, let us know it. So from here our answer began. Of the question. What question? Sir, how to transfer registers? How to transfer the data from register to bus? How to transfer the data from register to bus? From here the answer begins. Okay. First, let them know that do you know address bus? Do you know data bus? Do you know the control bus? If you know all these things, then we will transfer, na? If you don't know, how can you transfer? So for that, address bus. The address lines are used to designate the source and destination of the data on the data bus. Where my data is present, address line is going to tell that part. Address line is going to show where my data is present. Okay, fine, I came to know about the address via address line. In short, I came to know about the address where my data is present via address line. Who is providing address? CPU. Who is providing address? CPU. To whom? Maybe memory, maybe IO. To whom? Maybe memory, maybe IO. Okay. Now, there is something called as a data bus. Data bus is responsible for taking data. Data bus is responsible for taking data from where? Maybe IO, maybe memory. Okay, fine. Maybe from CPU also, right? Now, data lines provide a path for moving data among the system modules, right? These lines collectively called as a bus. So, like if you go on a higher level definition of a bus is what? Bus is a collection of lines. That is a bus, right? Every line is taking 1 bit at a time. Okay, fine. Now there is some point in the data bus, you need to understand that point. Although this is trivial only, but let us read it out. The data bus may consist of 32, 64, 128 or even more separate lines. It is not just a 8-bit line. No. It may have more than that. Then the number of lines belonging referred to as a width of the data bus. Let us say I have a 32 data lines. That means data bus width is what? 32-bit. I have 64 data line. What is my width? 64-bit. Okay, fine. Now I am giving you one example. You please understand this example. This is really good in order to understand the data bus part, how the data bus is really working. The example is saying, let us assume your data bus is having 32 line. But your instruction is a 64-bit. Data bus is having 32 line, but your instruction is a 64-bit. Data bus. How many lines? 32 lines. But your instruction size is a 64-bit. That literally your instruction is going to be stored in a 64-bit. Now can you tell me, at a time 64-bit will come? At a time 64-bit will come? No, at a time it won't come. So within an instruction cycle, we need to knock the memory module twice. The first time 32-bit, next time 32-bit. First time 32-bit, next time 32-bit. Because my data bus is of 32 line, That means at a time it can carry 32-bit data. The next 32-bit data will come in another cycle. Okay, we got to know like about the data bus, about this example also. Now, let me tell you over here one more thing, because here I remember one more concept is coming. One more concept is coming. Let me tell you over here. The concept is all about, you might have heard about this Indianness also. Indianness scheme also, right? It happens in this type of format. What I am saying? I am saying at a time your 32-bit data will come, and in the next time another 32-bit data will come. Okay, fine. But what it really means? That means let us say your first data of those 32 bits is over here, something like this. The next data is over here, something like this. This is also data, this is also data. How many bit data? 32-bit data. How many bit data? 32-bit data. And these two combine called as an instruction. They two are one instruction. See, I am telling you, this is just for knowledge purpose only. Whatever I am doing over here, it's for knowledge purpose only, because from this concept I came to know like one beautiful thing reminded in my head. That's what I am telling you over here. So even if you skip in your answer sheet, it is well and fine. Okay, they are not expecting you to please write about Indianness in the answer part. But let me tell you, maybe for interview purpose this is. Now which bit? This bit or this bit? Sir, you are talking about 32-bit will come, but which bit? This bit or this bit? Let us say every location in a memory. So these are memory location, right? These are memory location. Every location of a memory will have some address. Right? Assume that some logical address only. Okay. So because physically no addresses are present, they are all the logical, right? So now over here, let us say this is having some address 21. This is having address number 20. Okay, fine. Now, sir, which data? The data which is present at the address number 21 or the data which is present at the address number 20? Which data will come? So let us say your system is maintaining the little Indianness scheme. So Indianness is okay, fine, but Indianness is also having two types: little Indianness, then bigger Indianness, right? Over here, let us say little Indianness, your scheme is following. Little Indianness means the data which is present at the lower address will come. The data which is present at the lower address will have to store in the lower byte, right? The data which is present at the higher address will have to store in the higher byte. That means you know what is how does my data look like? You know how does my data look like? So let us say this is my data. So this data will be represent. Assume that this is 32-bit data. Okay, already I have written. I mean, it can show here 1 1 0 0 1 0. No. Some dot is there. That means 32-bit data. So in this location, my data 1 1 0 0 1 0 is there. Then which is your LSB? Then in next I have 1 0 1 0 dot means 32-bit. This means 32 bits. Okay, that means lower address will having this data. Higher address will having this data. So lower address, lower byte, higher address, higher byte. This mechanism is known as little Indianness mechanism. This mechanism is known as little Indianness mechanism. Okay, fine. Now the next mechanism is a bigger Indianness mechanism, which is a vice versa. That means lower address data is present on the higher byte. Higher address data is present on the lower byte. So just for information purpose, I have given you this particular thing, but need not to necessarily writing in your exam copy. Okay, but this is also an interview question. Do you know Indianness scheme? Little Indianness, bigger Indianness, big Indianness, right? And if you know, then can you tell me how does it work? So like this, because the data bus was 32-bit, instruction size was 64-bit, I came to know. That's what I am telling you over here. Need not to include in this answer. Okay, pardon me, I have taken your useful time, right? Now, control bus is coming. Control bus we already know. The control lines are used to control the access, to use the data and address line, that's all. Control line is using what? Control line is providing the control to address and the data format, that's all. Now the actual question is, sir, how to transfer the data from register to bus? How to transfer the data from register to bus? So this is how does it look like? The data is there in the register and we have to transfer in the bus, right? But the point is, we didn't understand anything from this diagram. I am just giving you the high level view. Data is present in the register, we are transferring on the bus. What do we really understand by that part? How the transfer is taking place? This is what we need to understand. For the same reason, I am going to show you the beautiful animation. Let us understand. So we both will understand together, okay? Don't leave me, don't leave me. Let us understand, my register size is 4-bit. What is my register size? 4-bit, okay? I want to transfer the 4-bit data. Where I want to transfer? I want to transfer in bus, fine. So let us say I have 4 registers also. I have 4 registers, and these registers are having 4 4-bit. I have register A, B, C, D, and in every register, how many bit? 4-bit, 4-bit, 4-bit. Now how to transfer this data in a bus? For that, I have taken multiplexer. In short, we called it as MUX. In short, we called it as MUX. Again, this MUX, this MUX, you have seen this MUX. Where? In digital logic. Again, the digital logic picture comes into the picture of a COA. That's what I am telling you. Like I am assuming that you have a knowledge for a digital logic at least at some threshold level. Okay? That the moment the decoder came, at that time I told you, like if n input to power n output. In the same way over here also, how the MUX is working, I am assuming you know this part, okay? Okay guys, if you see, this is a MUX, and now if you see MUX inputs are 4, that means the MUX is a 4 cross 1. How many input? 4 input. How many output? 1 output. 4 input, 1 output, what should be the number of select line? What should be the number of select line? If we have 4 input, the number of select line should be 2. Now let us do some mathematics. Let us say my MUX is 16 cross 1. 16 cross 1. Now if I ask you what is a select line? Can you tell? Please tell me first. 4, because 16 is what? 2 power 4. 4 select line. With these 4 select line, you can access any of the 16 input at the output. I hope you know MUX very well. Just now I have given you one basic introduction about the MUX. Okay, you know it, right? One last time let me ask you. I have 2 power k input. Now out of this 2 power k input, I want to take one of the input at the output. How many select line I required? Please tell me. I have 2 power k input. Out of these 2 power k input, I have to show one output. How many select line I required? I require k select line. K select line. I think now you are familiar. We both are on the same platform. Let us go ahead. Fine. Now how my register is going to be connected? Register. This is my register A, having 4-bit. Now see how it is connected. If you understand it, how it is connected, game over. You will get to know how the transfer takes place. Now see, this A register, this particular bit is going to be attached with MUX 0 input. The register A, the second bit, is going to be attached with MUX 2 0 input. This is MUX 1. This is MUX 2. The register third bit is going to be attached with MUX 0 third input. In the MUX 3 0 input. In the same way, this particular line, as you see here, from the fourth bit it is going to be attached at MUX 4 0 input. That means whenever I am accessing register A, what input I am triggering inside the MUX? I am triggering the 0th input. Whenever I am accessing the register A, what input I am triggering inside the MUX? I am triggering the 0th input. In the same way, if I want to attach the B register over here, what should I do? See, actually in the 4-bit register diagram, everything needs to be linked. But if I link over here, it looks clumsy. That's what I am removing it. I will manually draw it. I am removing it, I am manually draw it. Now see, before removing this part, let us see this select line also. So if I have 4 input, how many select lines? 2 select line. Now MUX we know only one output. Hold on. Please tell me. If I provide select line input 0 0. If I provide select line input 0 0. Input select line. If I am writing 0 0. If I am writing 0, 0, so you know the concept of mux, right? If I am providing 0, 0, which location going to be accessed? The location number 0. The location number 0. Now that means this particular location is going to be accessed. This particular location is going to be accessed. If the 0th location is going to be accessed, what is the output? The 0th location thing. What is this 0th location having? This is having this data. A register, this data. What is this data? 1. 1. Now, look. Over here in the mux 2, 0th location is having which data? The data, I think 2. So this is having 2. Now this mux having which data? 0th location is having which data? Data 3. In the same way, this mux having which data? Data 4. Now tell me. Register can able to transfer its data through bus or not? Register is able to transfer its data through bus or not? It can transfer. It can't transfer via mux. Now another question is coming. Let us say this time A register transfer. Now if I ask you, how can you link register B? How can you link register B? How can you transfer the data of register B? How can you transfer the data of register C? How can you transfer the data of register D? I'm asking to you. Let me erase it. Over here, if I show you the B register data on the bus, how can it be linked? This particular should go at the input 1. This data should go at the input 1. This data should go at the input 1 of mux 3. This data should go at the input 1 of mux 4. Yes or no, yaar? Now, fine, it is there. Now tell me. Now I am providing 1, 0. In the select line, I am writing 1, 0. In the select line, I am writing what? 1, 0. The moment I am writing 1, 0, that means which input I am going to access? I am going to access which input? I am going to access the input 1 inside a mux. Inside every mux, I am going to access the input 1. That means what? The data 1 is going to be here. Data 2, data 3, data 4. I think you got to know. Now. Now let me make it short. Here is my select line. You please tell. In the select line, if I am writing 0, 0, which data you will see at the output? Data of register A. In the select line, if I am writing 0, 1, sorry, in the select line, if I am writing 1, 0, if I am writing 1, 0, that means which data? B. If I am writing S1, 1, S0, 0, C registered data. If I am writing 1, 1, D registered data. Yes or no, yaar? Yes or no? I think this thing you should know. Because when I am writing 0, 0, at every mux, 0th input is going to be triggered. And mux A, every bit is going to be connected with the 0th input of every mux. When I am writing 0, 1, then 1th, the number 1 input present in all the mux is going to be triggered. And at number 1, input is going to be connected. Which input? Register B data. In the same way, register C present at the second input of every mux. That's what register C output will be there the moment you will provide 1, 0 at the select line. I think you are with me. Till now. In the same way, D, when you are providing 1 word, the D register is on the output. The D register is at the output, because this is how the your mux is working. Okay, fine. Now we got to know something. About how to transfer the data from register to bus. This is what your question was all about. How you are going to transfer the data? Yes or no, yaar? Now let us find some conclusion via that diagram. The conclusion is, in general, a bus system will multiplex k register of n bit, each produce an n line in a common bus. What do you understand? I am not assuming you understand anything. So for the same reason, I have written 2 more lines. You please understand this line. Okay, these are easy. The number of multiplexer needed to construct the bus is equal to n, where n is the number of bit present in the register. What he is saying? He is saying the number of mux required depends on number of bit present in the register. Let us say I am saying my register is having 8 bit. How many mux require? 8. my register is having 16 bit, how many mux require 16, like that. This is the first point, important point I am concluding. Can you see this diagram? The register is having how many bit? 4. Number of mux require 4. Register having 2 bit, number of mux require 2. Like that, like that. I think now you are comfortable. I think now you are comfortable. So number of mux depends on the number of register. Okay, fine. Now number of mux depends on the number of bit in a register. Number of mux depends on the number of bit in a register. Okay, fine. The second point is coming. The size of each multiplexer, be k cross 1, since the multiplexers k data lines. Why k cross 1? Because k is the register, number of register. In the first line, this is what you are not understanding in the first line. So they are asking a bus system will multiplex k register of n bit. That means every k register, every register is having n bit. Every register is having n bit, each to produce an n line common bus. Yes or no, yaar? Now you can combine these two lines. This line is a conclusion, assertion, reason. Okay, fine. Let me give you one beautiful example present on your standard book, Maurice Mano. Let us see this example. Nothing. Let us say this is an example. If I have 8 register of 16 bit each, then I am asking you the next question: how many multiplexer required? What is the size of each register? 16 bit. So number of multiplexer? 16. That's what here it is written. 16 multiplexer required. Next, one for each line in the bus. Each multiplexer must have how many data input? 8 data input. 8 data input must be there because number of registers are 8. That's why 8 data input. Now if 8 data input lines are there, what is the size of mux? 8 cross 1. Okay, fine. So this type of question may be formed. So this is the conclusion of everything. If someone asks you what is the number of mux, it depends on number of bits in a register. What is the size of mux? It depends on number of register. I think you can conclude these two things. Nothing, everything is over, right? Fine. Now we have seen two popular questions. The first question we have seen about your digital computer, the basic blocks of your digital computer. The next question we have seen how register is going to transfer its data via bus. Yes or no? We have seen this part. Okay. Now these are all the important topics. Now in next there is one more popular question is coming. Many times they have asked in some fashion. What are all those fashion? Let us look at it. Explain in detail micro operations. What are all the possible operations present inside your CPU? Discuss logic micro operation. What do you understand by this logic micro operation? Discuss arithmetic micro operation and shift micro operation. Okay, all these things we have to understand with this particular part. So this is the unit 1 and this is the you can say the third important topic about the micro operation. Let us understand these micro operation. So over here in a micro operation you have two major category: arithmetic micro operation, shift micro operation, right? Arithmetic micro operation and shift micro operations. Okay, fine. And there are some logical micro operations also. All these things are there for sure. These two are important, arithmetic and shift. We'll see those part. So in a basic arithmetic micro operation, we came to know arithmetic and shift. Now I'm telling you about the arithmetic micro operation. What are all the arithmetic micro operation? There are 4 very basic micro operation: addition, subtraction, increment, decrement, like that. These are 4 fundamental basic arithmetic micro operations. Some additional micro operations are also there. What are those? Sir, you can add with carry, you can subtract with borrow, you can transfer and load. These are all also the micro operation. Okay, fine. We came to know about what are the types of your micro operations present inside the CPU, all these things. Again, one more thing guys, like when I discuss again about the instruction, then I tell you like what are all the instructions. Then inside the instruction, these micro operation, how we can do it, right? But here I just want to give you a very brief view of those micro operations because it is there in the unit 1. It is there in the unit 1, right? Okay. Now I want to give you just a summary of all the possible micro operations present. Let us look that part. So there is something called as a micro operation for addition. Let us say I want to add the data present in R1 register, I want to add the data present in R2 register, right? And then that needs to be, go in the R3 register. Data in R1 register, data in R2 register, it has to be transferred in R3 register after adding. These are the content, now how to read these things, content of R1 plus R2 transfer to R3. Let us see this micro operation R1 minus R2. That means what? Content of R1 minus R2 transfer to R3. R2 dash, that means what? Complement the content of R2. And we know all these complement thing, right? Because we have seen in the digital part. Anyway, if you haven't seen, then we will see in our third unit. Third unit was all about data representation. Inside data representation, in the computer arithmetic, we are going to see how to take those complement and all those things. But if you look this particular person, this is nothing but 2's complement the content of R2. 2's complement the content of R2. So this R2 dash is a complement, and if we add 1 to it, that is nothing but 2's complement. And please you complement it and then transfer to R2, right? You just complement, that means you just complement it. Which complement? 2's complement. And I am assuming you know 2's complement because it is there in the digital logic. Okay. Now look at this part, R1 plus R2 dash plus 1. Okay sir, okay, we got to know this is 2's complement. Now what this person is doing? He is adding R1 content plus R2 dash plus 1. That means R1 content plus 2's complement of R2 content. Again I am repeating what this person is doing. He is adding R1 content plus 2's complement of R2 content and then transferring to R3 content. Why adding? Okay, if he is adding also, then what it is written? It is written subtraction, yaar. Arey? He is adding here, but we are writing subtraction. What is this? What is this? Because. What do you think? What do you think? Do we perform subtraction inside the CPU? No, big no. For the same reason, complements comes into the picture. I have seen in some lectures, people ask, sir, why complement? Why complement? Why we are studying complement? This is the reason. Because there is nothing like minus. There is nothing like minus. Minus is there in our human behavior. Inside the computer, he doesn't understand minus. He understands only minus number in terms of complement. That's the reason we read complements. Complement is the representation for a negative number. Whenever the negative numbers are coming, my CPU is complementing that. So which complement? 2's complement. 2's complement. Sir, why 2's complement? Why not 1's complement? 2's complement better. 2's complement better. 2's complement having more range. It's more good. Less error. That's why it is popular also. Your compiler, whatever you code, it's internally, it is following what? It is following the structure of 2's complement. It is following the structure of 2's complement, man. Now, you understand this part? No, literally you don't understand it. Let me tell you this part. Let me tell you how it is subtracting. If you understand this part, game over, everything over. For understanding this part, I am just asking you, you know 2's complement? Yes or no? I think you are saying yes because it is present in the digital logic. Now, how this complement is helpful in the subtraction, over here if you see, everything will be clear. Let us say I want to do 5 minus 3. 5 minus 3 I want to do. I am asking you one thing. How 5 can be represented? How can you write 5? How can you write minus 3? In 2's complement I am asking. Please careful, in 2's complement I am asking. How you are going to write 5? Some are saying slowly, sir, 101. Some are saying slowly, 101. Arey no, I am asking in 2's complement. 5 is written as 0101. My next question, how can you write minus 3 in 2's complement? How can you write minus 3 in 2's complement? Can you write 3 in 2's complement? Can you write 3 in 2's complement? Yes, 3 is this. In 4-bit, 3 is this. Now how to write minus 3? You take the 2's complement of plus 3, you will get minus 3 in 2's complement. Arey, this is how we study, right? Now, minus 3 is all about this part. Minus 3. So if I have to write minus 3, I will write this. So just take 2's complement. 2's complement is what? 1, 0, 1, 1. This is the 2's complement of this particular plus 3. And this is minus 3. This is plus 3. This is minus 3. Don't say this is minus 5. Arey nahi, this is sign magnitude. If you are writing in terms of sign magnitude, then this is minus 5. Then this is minus 5. Right? We are talking in terms of 2's complement. In 2's complement, this is minus 3. This is minus 3. Okay, fine. Now, write minus 3 here. Write minus 3 here. Let me write minus 3 over here. So, minus 3, how can I write? 1, 1, 0, 1. Add it. See this person. See this person. Who is he? 2's complement. I'm doing what? Adding. What was my operation? Subtracting. But what I am doing here? Adding what? The content of R1. Let us say this is my R1. This is my R2. R2 content is this, R1 content is this. Now let me add it. What I am getting? See, 1, 1, 1, 1, 1, 1, 0. I hope you know the binary addition. Again, it comes into the digital. See guys, why I am saying again, because COA is built on the digital. You know digital first, then you come on the COA. Okay. Now 1, 1, 0, 1. Now 1 is here. 1, 1, 0, 1. 1, 1, 0, 1. Now this is the output over here, which we used to discard. You take this result. What is this result, man? And this result where we are transferring in R3. Okay, fine. We are transferring in R3. Can you tell me what is this in 2's complement? Please tell me in 2's complement what is this person? This person is 2. 2. Can you tell me what is 5 minus 3? 2. That means there is nothing like negative here. There is nothing like negative. Everything is addition. Let me tell you, even multiplication is not multiplication. Multiplication is shifting addition. Multiplication is what? Multiplication, shift add. This is multiplication. There is nothing called as, see, let us assume, you just use your common sense. For every operator, if we started designing a new circuit, arey, how complex our motherboard look like, yaar? That's what. Adder is important. Your plus addition is important. Over here, this is 2. Okay, this is one of the example. Take any other example. Whatever you want to give, you can give. Okay, take any example. Let us say you want to take something like, sir, I'll take plus 10. I'll take minus 13. Something like that you have taken. Any example you take here. Just follow these rules systematically, you will get it. Okay. What we are learning? We are learning this part. Sir, you are doing subtraction, but over here it is written addition. Just to tell you this part only, I am doing this thing. Sir, over here subtraction written, but the symbol is addition. Why? For this part only I am telling all these things. Okay, fine. Plus 10 minus 3. In the system, there is nothing like minus. Whenever the CPU is looking at the minus, he is converting it into 2's complement. Okay, fine. How to write this 10? How to write 10 in 2's complement? How to write 10 in 2's complement? Let me write. Array 1 0 1 0. Don't say. Put here 0. This is 10 in 2's complement. In 2's complement representation, this is 10. Now, how to write minus 13? See, how to write minus 13? First, do you know how to write plus 13? Do you know how to write plus 13? So, 1 1 0 1. So, I think let me write it clearly. One 1 0 1. This is plus 13. Okay. In 5-bit. This plus 13. Now, take 2's complement in order to get minus 13. Now I have to take 2's complement. Let me write minus 13. So minus 13 is your 1, 1, 0, 0, 1. This is your minus 13 in 2's complement. Okay, fine. Now add it. Why I am adding? Because see, this is addition. Array, there is nothing like subtraction inside the CPU. Don't think I'll subtract. No. Subtraction is for manual purpose, yaar. For CPU, add. What add? Array, take 2's complement and then add. Okay, fine. Just do it. Add it. 1 0. I'm having 1. 1 1 0 1. Then 1. Then 1. Then 1. Okay. What is this? Sir, this is minus 13, sir. You are wrong, sir. This is minus 13. Arey, no. How can you say like that? How can you say like that? How can you say this is minus 13? No, man. What is this? What is this? Sir, it is written 2's complement. And this is a negative number. It is a negative number, yeah. Why? See MSB. MSB is one negative number. Can you tell me directly? Can you tell me directly? No. If it is a negative number, how can you tell me directly? You please take the 2's complement first, then you will tell. Arey, how you are writing minus 13? First you are writing plus 13, then you are taking 2's complement, na? First you are writing plus 13, then you are taking 2's complement in order to find what is minus 13. In the same way, if it is a negative number, how you define a negative number? By looking at MSB. Now if it is a negative number, how can you tell me directly? You can't tell me directly if it is a negative number. Take 2's complement first, yaar. Now take 2's complement first. See. Now MSB is 1, the number is negative. Now take 2's complement first. That means 1, 1, 0, 0. What is this? What is this, yaar? 3. That means the result should be minus 3. Can you tell me what is 10 minus 13? What is 10 minus 13? It's minus 3, yaar. Minus 3, minus 3. Okay, fine. That means this minus is for us. And the 2's complement addition is for computer. This minus operator is for us. But 2's complement addition is for computer. Now I think you better understand this part. The next part is coming, increment. R1 plus 1, increment. And R1 minus 1, decrement. Okay, fine. Sir, we came to know about the basic micro operation. But there are some of the popular question inside the micro operations only. Inside the macro operation only, there are some of the popular question, right? Okay, the popular question inside the micro operation, can you design a 4-bit binary parallel adder? That is also known as 4-bit triple carry adder. Can you design that adder? How to add 4-bit number? That means addition micro operation we are going to study. So first of all, let me tell you how manual, how we people will do. So let us say over here, full adder is responsible. So again this, see, decoder comes, I ask you, you have seen in the digital. Multiplexer come, again I have requested, you have seen in the digital. Again this guy, full adder is coming. Again I am requesting, you have seen in the digital. Full adder, half adder, all these things are digital thing, right? Okay, full adder come. Now we already know full adder takes how many input? 3 input. So 3 input you can see or not? 3 input you can see or not? Okay. Now it is providing, how many output it provide? Can you tell me, full adder, how many output? 3 input, how many output? 2 output. One is sum, other one is carry. Okay, fine. So this entire section is for one full adder. This section only. 3 input, 2 output. C in A naught, B naught, S naught, C1 is the output. These 3 are the input. Okay, fine. Now let us assume, let me take a number parallelly. Let us say my A register and B register. My A is having something like 1101. My B is having something like, let us assume 000010, like this. Okay? If I add, what is my result? What is my result? The result should be 1, 1, right? Result should be 1, 1, 1, 1. That means 13 plus 2, 15. I am taking unsigned number and this is the result, 15, 15, okay. That means A naught, if I ask you what is my A naught, 1. What is my B naught? 0. Now this is a sum. What is your S naught? 1. Fine. Is there any carry? No. No carry output. Is there any carry input? No. Everything is fine. Let us say if I ask you to optimize it, can you add here? Can you write half adder or not? Array, at the starting for this first bit you can take half adder because when you are adding without carry, array, you are adding these two only, no? There is no carry, there is no role of carry. Then even half adder will work perfectly. In the first bit, for adding n bit number, in the first bit, half adder will also work. Okay, fine. The output is C naught over here. Now, the A1, can you tell me what is A1? 0. Can you tell me what is B1? 1. Now if I add 0 and 1, what full adder is doing? Adding. If I add 0, 1, what is the output? 1, 1, 1. There is no carry, right? That's what? C1 is 0. This is C1, right? This is 0. That's what? I am getting what? 1, 0. If I add, I am getting 1 again. S1 is what? 1. 1. What I'm showing you? I'm showing you the block diagram, that's all. This is what the examiner is asking. Can you draw the block diagram of 4-bit adder? Can you draw the block diagram of 3-bit adder? Like that they are asking. Okay, fine. Now after that, is there any carry produced? No. Can you tell me with this example, what is A2? 1. What is B2? 0. Now if I add 1 plus 0, what I am getting? 1. What is the carry output? 0. In the same way, what is my A3? 1. What is my B3? 0. If I add 1 0, what I am getting? S3 1, C4 0. Can you tell me what is S3, S2, S1, S0? 1 1 1 1. That means what? S3, S2, S1, S0 1 1 1 1. So this is what they are asking. Arey, nothing is there. The only thing is, do you know how to represent this registered data? That's all. Okay. So this diagram is also known as 4-bit binary parallel adder or 4-bit triple carry adder. Now in this particular diagram there can be so many questions, yeah. There can be so many questions, but let us stick with the b.tech curriculum and stop ourselves to here only. Like they may ask like this, when you really want to dig this question, they may ask like this, okay, in this 4-bit binary parallel adder, how many full adder we can use? You can say 4. How many half adder you can see over here? How many half adder you can see over here? Can you give me? Can you tell me full adder is a combination of what? How many half adder? In a full adder, how many half adder? I think you remember the digital logic, 2, right? 2. Then how many full adder? 4. How many half adder? Internally you should know full adder. How does it look like? So if these are 4 full adder, then 4 into 2, 8 half adder. 8 half adder is there, right? 1 with OR gate. So full adder is implementation of 2 half adder with OR gate. Arey, yes or no, yaar? Already these things we already know in our basic subject. Okay, fine. Now this is the animation part of adding these bit. So I have already taken it. I told you like A0, A1, A2, A3, B0, B1, B2, B3, right? So it will produce something. This thing only I am going to show you in the animation. That's all. Nothing new. It will give S0 carry C1, something like this. It will give S1 carry C2, something like this. It will produce S2 carry C3, something like this. It will produce S3 carry C4 like this, and you can take it as a C0 input. Okay, fine. So this is how it works. Initially we have no carry. That's what C0 can be 0. That's what I was asking. In the first bit, can I take half adder? Because half adder is responsible for adding what? 2 bit. That's what my question at the first was. In the place of first bit, can I take half adder? I can take half adder. Why? Because in the first bit I have only 2 input. 2 input is really required. What C0 is doing? Nothing, having 0. Okay, fine. Now this is the carry generated over here. That's what written here, C0. Now if I am writing here C0, you please change it. Now this will be C0, this will be C1, these are C2. Now this will be C3. Okay. Now this is nothing but your C in, or in some textbook it is also written as C out, like that. That means carry out. C in, carry out. I think everything is fine till now. Now these going to be added. We will see this result. Then the carry is propagated over here. See the flow. Because tell me again, one more question is coming. Tell me, without this carry, can you add the second bit? Without this carry, can you add the third bit? No. That's what it is also known as ripple carry adder. That's why it is also known as ripple carry adder. This is the reason. That's what the heading I have mentioned. 4-bit binary parallel adder or ripple carry adder, like that I have mentioned. Yes or no, yaar? Okay, fine. So I got to know that you know these things. Now you came to know about adder. This is the right time. In some of the PYQ I have seen, they are asking, do you know adder subtractor circuit both? Okay, you know the adder circuit, but do you know adder subtractor circuit both? Can you draw that circuit? That means they really want to check whether you know how the subtraction work. How does subtraction work inside the circuit? They want to check that part. Let us see and understand that part. So if you see the same diagram I have manipulated in some way, the same diagram I have manipulated in some way, I have added one more unit called as XOR, called as, again this unit is from the digital. Okay, that's what I am repeating again and again, digital, digital, digital. If you really want to grasp COA, be prepared, be good in digital. If you are really good in digital, COA path is easy. Anyway, let's come back. So this is XOR. I have taken XOR gate over here. Okay, what XOR is doing, we will look all these things. But how I have modified it? This is my full adder. 3 input for sure. But this B0 I have taken with XOR. In the adder circuit, B0 was directly getting inside the full adder. But in the adder and subtractor circuit, B0 is getting inside the XOR. Not only for this full adder, for this bit and this bit. Everything. Now I have taken XOR, a 2 input XOR. The first input is responsible for taking your content of the B register, like B0, B1, B2, B3. The second input is manually we are giving depending on the operation. Let us say I want to do the addition operation, then what input I should give? I want to do the subtraction operation, what input I should give? This is what you need to understand over here. That's what the heading written, adder and subtractor. The heading is adder and subtractor. Just to tell you this part, let me tell you, I am assuming you already know XOR. But still, as I told you about the decoder, as I told you about the multiplexer, in the same way, let me tell you about something about XOR. Let me tell you over here. See, if let us say, if I am writing A XOR B, what it literally means, its equation is saying I am nothing but A complement B plus AB complement. Okay, fine. Are yes or no? Now, let us assume if I am doing A XOR 0, what I am having? You please put it over here. So A is A only, that means it will be A bar dot, B will be now 0 plus this. So now this is A only, that's what A dot, B bar is what? 1. So if I am XORing my input with 0, what I am getting? A bar dot 0 is what? 0. A dot 1 is what? A. What is A plus 0? A plus 0 is A. A plus 0 is A, right? Okay. In the same way, again I will ask you another question. Can you tell me what is A XOR 1? Can you tell me what is A XOR 1? A XOR 1 is A bar dot 1, right? Plus A. So what I am doing? Hold on. Let me write sequentially so that you will understand with the help of formula only. This is A bar, B is directly 1 plus this is A now. Now this is B bar, that means 0. That means what? This person gone, he is 0. What is this person? This person is A bar dot 1, that means what? A bar. A bar plus 0 is what? A bar. That means if I XOR 1 with A, the output is A bar. If I XOR A with 0, the output is A. I think till now everything is okay. Now you got this thing. Now you please tell me, if I provide my input over here 0, that means here also 0, here also 0, here also 0, here also 0. You please tell me, if these two inputs are 0, then what is the output of your XOR? The output of your XOR is B0. Just now we have seen. If I XOR with 0, the same, whatever the input I am providing, the same as the output. Here B1, here B2, here B3, like that. Now it is behaving as adder, array, A0, B0 directly coming inside the full adder, A1, B1 coming inside the full adder, A2, B2 coming inside the full adder, A3, B3 coming inside the full adder. That means what? It is behaving as an adder. Okay, we understood this part. But can you tell me about the subtractor? Can you tell me about the subtractor? See, look at this person, subtractor. How can you manage subtractor in the same circuit? Give here one, give here one, give here one. One is here, one is here, one is here, one is here. Now please tell me, what is B0 XOR with 1? B naught XOR with 1 means B naught complement. Array, just now we have seen, in the same way B1 XOR with 1 is B1 complement, B2 XOR with 1 is B2 complement, B3 XOR with 1 is B3 complement, like that or not? Okay, fine. Now tell me this part, If I write, what is my S naught? What is my S naught equation? S naught is taking, see what S naught is taking? S naught is taking A naught and B naught complement, and here also 1, because I am providing 1, right? 1. Can you tell me what is this? Just now we have seen in the micro operation. What do you understand by this part? I assume that you know it. Array, please say. What is this? This is subtraction. What is the heading? Subtractor. Array, we got to know. What is this? Subtraction is going on, man. Adder we understood. Subtractor also understood. When this circuit is behaving as adder? When we are providing 0. When this circuit is behaving as subtractor? When we are providing 1. Adder providing 0, subtractor providing 1, gone, over. That means we came to know about the adder circuit individually. We came to know about the adder and subtractor individually. What is there? Nothing. Okay, sir. Adder subtractor over. Some questions are directly like this. Can you draw arithmetic circuit? In that arithmetic circuit, please try to take most of the arithmetic operation. In that arithmetic circuit, try to take most of the arithmetic operation. Can you draw arithmetic circuit? So for your reference, I am going to draw arithmetic circuit. Arithmetic circuit. Okay. So before showing you that part, okay. Okay. Since we have a limited time, we have to finish this part also. Let us finish this part. This is the end game. Picture over. Unit 1, important topics over. At least in unit 1, the first part, important topics over. Arithmetic circuit. So in the arithmetic circuit again, we have seen in adder also, subtractor also, full adder require or not? Full adder require. That's what I am taking, full adder. My arithmetic circuit, I am assuming whatever the operation I am going to do, I will do on the 4-bit only. Whatever the operation I will do on the 4-bit only. That's what I have taken. For full adder. Okay, fine. Now the next is one of the input inside the full adder. Directly I am giving. Let us say this is my register A, having input A0, A1, A2, A3. My register A having input A0, A1, A2, A3. So let me name it. What is the input I am having? A0, A1, A2, A3. Fine. This is coming over here. Everything is okay. Array, no mind involved, yaar. No mind involved. This is full adder. I am taking it as A only. Okay, fine. Now next. I am taking mux because I need to implement so many arithmetic operation, right? My inputs will be so many. I have to check what are all the operation. Let us see. 4 input mux is there. Over here also 4 input mux is there. 4 input mux is there. If 4 input mux is there, how many select line? 2 select line. Now these input, how they are connected, let me show you how they are connected. So over here, these 2 select lines are there. 2 select line I have drawn with green and one with you can say dark yellow. Now about 0, 1, 2, 3 input, I am going to connect. Let us say this is my B naught. Let me take. This is my B naught. Another input. This is B naught complement. Again, I am having this blue as a B naught, this is B1, and the white one is the B1 complement. Blue, B2, white, B2 complement. Blue, B3, white, B3 complement, like that. So what we are designing, first we are looking at the input parameters, then we will understand the working. First I am looking at the input parameters, okay. Now after that, this particular line, let us assume this particular line is 0. This particular line is 0, this particular line is 0, this particular line is 0. Okay, fine. Okay, the next line is 1, next line is 1, like that it is going to be. If I ask you, let us say, understand this mux, let us understand. If I ask you, this is 4 cross 1 mux, how many input? 4. Can you tell me what is the input at 0? Input at 0 is B naught. What is the input at 1? Input at 1 is B naught complement. What is the input at 2? Input 2 having 0, 0. Input at 3, input 3 is 1, 1. I think now you are comfortable. Let us assume I want to access the input present at the second point. What is the select line value I have to give? If I have to trigger this second input, what is the select line value? I need to give 1 0 or not? 1 0 or not? That means higher bit will have 1, lower bit will have 0. If I am providing 1 0, that means in every mux, second input is going to be trigger, because select line is 1 0. I think till now you are with me, you have to with me, there is no other option. Are yes or no, yaar? Fine. Okay, so I believe you understand this part. Now this is the right time, for adding the output of these mux to the full adder. And let us say the carry has been propagated. Arey, this circuit is for adder or not? Don't think it is a complex. That's why I have animated it one by one, yaar. Don't think it is a complex. It's a full adder. This is a one input, A0, A1, A2, A3. This is the another input. This another input is coming from the mux. In the mux also 4 input is there. B complement 0, 1. Okay, fine. Till now everything is fine. Now I need to perform some arithmetic operation. How I can perform some arithmetic operation? For that, first of all, see, can you see my output? From every full adder, my output is coming like that. Now let me tell you some operation. Then I'll execute those operation in this circuit. First, let me show you those operations. So if you see this person, S1, S0, select line is having 0, 0, and carry is having 0. Then this person named Y. Who is this person? Who is this person? Y. Who is this? Y. Let me show you where Y is there. Here Y is there. Y is this one. Y. What Y is doing? He is the output of mux. Who is Y? Y is the output of mux, yeah. Now, if I ask you, let us say this output depends on what? This full adder depends on what? This full adder output depends on C0, A, Y. This full adder D1 depends on what? C1, A, Y. Arey, it will add these three or not? In general, I am writing, in general, if I write my D is nothing but A plus Y plus carry. Okay, A plus Y plus carry, this is my D. Arey, yes or no, yaar? A is not going to be changed. Every time we have provided one input directly. But Y is going to be changed, man. Y is going to be changed. Y depends on the multiplexer output. That's what it is going to be changed. Now, let us see. You please write this particular formula. Now, everything is easy. Let me show you how the things are easy now. See, let us talk about this row. S1, S0, 0, 0. Cin is also 0. Then we will figure out what are the operations coming out. If all three are 0, 0, what are the operations coming out? Let us see. All three are 0. That means we are writing here S1, S0. This is my S0, S1. They are 0, 0. That means mux input 0 going to be trigger. 0 going to be trigger. In 0, what is there? B naught. In B naught. So here B1, here B2, here B3. That means Y is nothing but B. What is A? What is A? A is nothing but A. A is A only, right? Like, see, I'm taking A as combined form A0, A1, A2, A3. Why is, this is nothing but a combined form of B0, B1, B2, B3. Ci. But what I have provided in Ci? 0. What is A plus B plus 0? This is nothing but addition. Addition of what? Two register A plus B. So this is what written here. D is A plus B addition. Are yes or no, yaar? Now see, second row. 0, 0, 1. If I am writing 0, 0, 1, that means S1, S0, 0, 0, C in is 1. Let us see what is happening. If I take this is 0, 0, and this particular person has 1. So this Ci will be 1. They two will be same. That means addition of content of A and B, addition of A and B with carry. That means addition with carry. Let us see what is the comment. A plus B plus 1 add with carry. I hope you are getting. Now look at this part also. 0, 1, 0, 0, 1, 0. So 0, 1, 0 is there. What do we understand by this part? If I am providing S1 as 0, S0 as 1, C in as 0, what I am getting it? Let us see that part. So S0 is so what we are having? 1, right? 1 means this is 1, this is 0. Okay, now I am providing this part. So let me erase these things. Now this is gone. Let me erase these part. Maybe some new factor will come, right? Okay, now let us understand what is happening. Let me take another pen. Okay. 1, 0. That means in the mux, which input is got selected? You please tell, you please cooperate. 1, 1, 1. One input got selected. 1. Now can you tell me what is the one input? B complement. So over here B0 complement. Over here B1 complement. Over here B2 complement. Over here B3 complement. What is there here? That means in general Y is what? B complement. Is it visible? So this is what? B complement. This is A only. And what I have provided in place of C in? Let us say I have provided 0. What is this? This is subtraction with borrow. What is this here? Subtraction with borrow. Array, it is not subtraction directly. It is subtraction with borrow. What is subtraction? When you do the 2's complement. Array, when you do the subtraction using 1's complement, you need to take care. You need to take care of the result. But with the 2's complement, everything is simple. That's what people are following 2's complement. Okay. So this is a subtraction, but using 1's complement. In that we have to take borrow. That's what it is written. Subtract with borrow. Over here, if I provide in place of C in 1, this S1 S0 is same, but in place of C in 1 I am providing. Let us see what I am having. In this place I am writing here 1. That means, can you tell me what is this? This particular person is nothing but 2's complement. If I add 2's complement with any of the content, that is nothing but subtraction or not? Subtraction. That means what I am doing? Subtraction. See what it is written? Subtract. Now let us understand. So we understood this row. Let us understand this row. 1, 0, 0. If I am writing 1, 0, 0, what I really understood? Let us look at this part. Now here comes 1, 0. Let me remove it. Here comes 1, 0. Here comes 1, 0. That means 2. 1, 0. 1, 0 means unit 2 got selected. Unit 2, input 2. Output will be 0. Output will be 0. Okay, output is 0. That means what? A is A only, but Y is what? Y is having 0. Let us say carry in also 0. In the first case I am taking carry in 0. In the second take I am taking carry in 1. If I am taking carry in 0, what is this? My D is equals to A. What is that? Content of A is going to be transferred in D. This is written transfer A. Now next row is coming, this one. Let us understand. Again, everything is same because the select lines inputs are same. Now that means A is there, 0 is there, but carry in is 1. What is this? A plus 1 is what? A plus 1 is increment. I have incremented my content of register A by 1. That is what? See, let us say my register A content is 1, 0, 1, 0. If I add 1 over here, only one I am adding. What I am getting? 1, 1, 0, 1. What is this? 10. What is this? 11. Array incremented or not? Incremented. everything is fine. So what I am getting at the result? 11. 11 I am getting. Okay, fine. Now I think everything is clear at this part. Till this part everything should be clear, guys. Now look at this row. What I am having? 1 1 0. 1 1 0. 1 1 0. What is there I am getting? Let us see that part also. So the content is 1 1. C in is 0. Let us understand. And if you are sleeping, don't sleep. This is the really important part coming. Really important part coming. This part. Please wake up. Wake up. Now look at this part. Now I am providing my input like that. I am providing my input like that. What I am providing? I think 1 1 I am providing. 1 1. C in is 0. If I am providing 1 1, which input? Third input, third input, third input, third input. If I am providing 1 1, which input? Third input, third input, third input, third input. From mux. Now output will be 1. So these 0 will not be there. Output will be 1. Output is 1. Output is here 1 1 1. Now can you help me? A is A only. Always A is A because no change. What is Y? What is Y? What is Y? Y is 1 1 1 1. What is Y? Y is 1 1 1 1. What is C in? C in I am writing in the first case 0. Now what is this here? What is this? Can you tell me what is this? Let us understand what is this. Let us understand what is this. Let me take one example. Let us say as again my data is this 1 0 1 0. Now I am adding with 1 1 1 1. Let me add it. Let me add it. What I am getting? If I am adding with this part 1 0 1 0 1 1 carry 1 discard it. Okay, fine. What I am getting over here? 9. Array, what was this? 10. What is it? 9. That means what? I decremented or not? I decremented or not? If my Y is all 1, what? I decremented or not? I decremented. That's what it is written over here. It is written as a decrement. It is written as a decrement. Now, look at this particular part. The last part, last row. I am having what? 1 1. S1, S0, I am having what? 1 1. But the carry right now is 1. If the carry right now is 1, let us understand that part also. Carry over here is 1. Let us see. Carry is 1. Over here carry is 1. Array, what is this here? Array, nothing. You did this part already. You got 9. If you add 1 over here, what you will get? The same number. That means the content of A is not changed. The content of A is same. That means what? It's nothing but transfer because content of A is not changed, right? That's what it is written here. D is equals to A, transfer A, that's all. So these are all the basic arithmetic micro operation can be implemented with this particular circuit. Tell me, it is easy or not? It is really easy. Just you need to focus on that part. Each and every row I have explained you. If there is any problem, just go back and revise it again and again. Really easy, yeah. Okay. Now this is the time to end. I'll take you just 2-3 minutes more and I'll end it up. Okay. I need to discuss one more because after this micro operation will be over. At least the major portion of the micro operation will be over. In the micro operation, we have 3 types of micro operation. One is logical micro operation, arithmetic micro operation, circular micro operation. Now in each of the micro operation, I have two micro operation. Logical shift left, logical shift right, arithmetic shift left, arithmetic shift right, circular shift left, circular shift right. Now the moment I will start with the logical shift micro operation, let us see how does it work. How does it work? Let us see that part. So let us say this is my register. Array, check it. This is my register. Don't think this is my register. In the register, how many bits are there? 4. In the register, how many bits are there? 4. Now what I want to do? I want to perform logical shift left. So how the logical shift left will work? Look at this. Look at this animation carefully. The 0 will be padded on this part. This part. All the bits got shifted. 1 1 1. This is the logical shift left. Now again in the 4-bit register, if I want to do logical shift right, how does it look like? Look at this animation. All the bits needs to be propagated 1 bit ahead. Array, yes or no? Yeah, please say yes. This is so 0 padded on the MSB part in the right shift, 0 padded on the LSB part in the left shift. This is the logical shift operation. Now the next one is arithmetic shift left and arithmetic shift right. Let us understand this also. Let us assume again in my register the content is 1101. In my register the content is 1101. The name arithmetic says it will take care of sign. It will take care of sign. Now I want to do logical shift left. I want to do logical shift left. So it is I want to do, sorry, pardon me, I want to do arithmetic shift left. I am going left side. Same, in the same way, the way logical shift left was working. In the same way, see, in this fashion. So, but beautifully, I have taken these two bits same. Carefully, I have taken these two bits same because this is an arithmetic operation, right? And it is performed on the sign number. If it is performed on the sign number, so after shifting, the sign must be same. So let us say I shifted, sign is still same, but there need not be necessary always the MSB and the bit present next to MSB having the same sign, having the same value. This is not the always case. Let us say this is my now content. Now my new content is this. Again, if I do arithmetic shift left, what is the value? I'll get the value as this. 0 will come here, 1 will come here, 0 will come here, 0 will come here. Now tell me out of these two, tell me out of these two, the sign get changed or not? The moment your sign is getting changed, that means some error is there. In technical words, it's a overflow thing. It's a overflow things. So you need to be careful. When the MSB bit and the next bit next to the MSB bit, they both values are differ. That means whenever you will perform arithmetic shift, the sign will get changed. That means your result will become wrong. That means overflow is there, right? Okay, fine. Now arithmetic right shift, we need to maintain sign or not? Array, when we are doing the left shift, whenever we are losing the sign, then we are saying there is a overflow type of thing. There is a overflow type of thing, then we need to check that part. But if we are doing arithmetic shift right, then how to do it? Please remember, we have to maintain sign. If it is positive, let it be positive. If it is positive, let it be positive. How? In this fashion. In this fashion. The new content will be, because it was 0, the new content should be 0. If we are doing it in a right fashion, if we are doing it in a left fashion, then if this bit and this bit having same value, then everything is okay. If these two bits having different value, then there is a overflow, right? Okay, we got to know about this part. Then there is the next one, circular shift left, circular shift right, circular shift left, circular shift right. How circular shift is working? Let us see the animation. Nothing is there. Let us see the animation. See this part. The MSB content is going again at the LSB. Every bit is got left shifted, but the MSB content is going again in the LSB part. This is the circular shift left. Circular shift right, see how. So every bit propagated on the right side, the LSB content shifted on the MSB part. Okay. Now with this shifting operation, what we understand really, especially in the arithmetic shifting operation, what we understand really, we understood, sir, if we do left shift, that means we are multiplying. If we do right shift, we are divide. So with this shifting operation, in the shifting operation, what we can conclude, sir, if we are doing left shift, that means multiply by what? Multiply by 2. If we are doing right shift, that means we are dividing by what? Dividing by 2. Okay. So this is about shift micro operation. So I think, so because of this lag of time, guys, I have to stop over here, but let me tell you very frankly, we have covered the really important topics present in the chapter 1 first part. In the chapter 1 only, I think in the last part, in some of the universities, they have added the instruction cycle and interrupt cycle as well. But frankly speaking, instruction cycle and interrupt cycle, you can study in the chapter 2. Why I am telling you? Because in chapter 2, in unit 2, you have CPU design. The moment you understand CPU design, the moment you understand how the stack architecture is working, how the accumulator architecture is working, now then there is a right moment to understand how it is handling interrupt, how the instruction cycle is working, all those things. Okay. Hope you have enjoyed the session. Now you are very much confident in the unit 1. I am believing so. These are all some of the important topics present in our this computer organization and architecture with respect to unit 1. One more minute guys, hold on. I just recall, let me go at that part. Let me go at that part quickly, because I think I have shown you one numerical also, yaar. I want to finish it in 1 minute. This one. Just now we have discussed it, right? All our theory only. See. Now look at this question. Discuss the bus system for 4 register and explain. Now I think you are very much comfortable. Look at this next question. 8-bit register contained the binary value, this one. 8-bit register. I have shown you 4-bit, but they have given 8-bit. 100, 11100. Now they are asking what is the register value after an arithmetic shift right. Arithmetic shift right they are asking. That means sign must be maintained. Sign must be maintained. Okay, fine. That means if 1 is here, 1 should be there. You please propagate everything, because 1 is in the MSB, put it here, and rest all the things you propagate. All the thing you propagate, man, like this. So this is the output. You propagated everything you propagated. This is the output for the first part. Second, starting from the initial number, again you take initial number again. He is saying 100, 11100. Determine the register value after the arithmetic shift left and state whether there is an overflow. Now, for sure there is an overflow, because I told you if these two signs differ, then there is an overflow. No, actually, let me tell you, this question is present in the Morris menu, okay? But in the JNT also the people ask. What they do most of the time, they open the exercise of the Morris menu or the topic of the Morris menu, they will directly give in the exam. Anyway, it's really easy. Now, come over here, what we have to do? Shift left. Now come here. So this 0, 0 will come, 1, 1, 1 will come, 0, 0, 0 will come. Now see, since these two bits differ, that means overflow. And yes, overflow is there. At the initially the number was negative. After shifting, it become positive. That means it got errored. That's what? Positive number. Negative number converted into the positive number. That's what? Error is there, right? That means overflow is there. So in the next part, the answer is yes, overflow is there. Okay. Okay, guys. Thanks a lot. Thanks for being with me. I think we are now done. All the best for at least unit 1 concept. You please go through whenever you find time. One more time in this video. You will get everything. Okay. Watch it slowly. You will get everything. Okay. Thank you. All the best. Take care. Good night.